Hello everyone, welcome back. We continue studying chapter 2. Okay, today we studied the part 2. Part 2, equivalent single axle load, ESO. ESO is a result from analysis of traffic data. ESO is number of sand axles. ESO is the key parameter for handling the traffic load input in payment design. ESO is critical. Let's start on ESO right now. According to the Chinese design specification, there are 11 types of vehicles, and each of them has different axle configurations, width, and VCDFs. Obviously, great variety of vehicle axle load configurations loads cause different distress to payment structure. This alone creates a huge problem to payment designer. In order to handle this problem, the axle load equivalency method is utilized to convert the non-sand axles into sand axles. As a result, the complex traffic that are expressed with a single parameter, equivalent single axle load, ESO. In order to better understand ESO, we first discuss a few concepts. Sand axles, SA, equivalent load factor, ELF, and the truck factor, TF, equivalent single axle load, ESO. The sand axle load represents axles among the traffic flow. In Chinese specification, the sand axle is single axle on zero tails. The axle weight is 100 kilonewton, and the tail imprint pressure is 0.7 megapascal. The load area diameter is 213.0 millimeter, and the distance between the two circular loading area is 319.5 millimeter. Equivalent axle load factor, ELF, is the factor to equivalently convert non-sand axle load into the sand axle load according to their damageability. In other words, ESO equals ELF times number of non-sand axles. How to determine ELF? Many years ago, in 1950s, AASHTO road tests was conducted for different type of payment with considering different damage indicators. During 1980s, the similar studies were conducted in various European countries. Recently, the similar studies are also being conducted in Beijing of China. The testing road was built in 2017, and the preliminary data had been collected. Road tests are conducted on the identical road structure with the different loading conditions. One is the different loading of non-sand axles, while the other is the sand axle. When the payment structure was damaged at identical degrees, the traffic data was collected. ELF was calculated as the dimensionless parameters. The number of the sand axle is divided by the number of non-sand axles. For instance, the number of non-sand axles of 80 kilonewton is 10 million, while the number of the sand axles is 5 million. ELF of 80 kilonewton is 5 divided by 10 is equal to 0.5. Through analyzing a lot of the road testing data with similar weights and equivalent models for ELF, could be developed. Nowadays, there are various models for ERF variables. In this online course, we only introduce a model from Chinese specification. This equation shows the ERF model from the Chinese specification. Obviously, PS is given. PS equals 100 kilonewton. PI is the key variable which depends on the specific project. In order to use this model, the X load related coefficient alpha and payment related coefficient n should be determined. This slide shows how to determine alpha and n based on the data from the lab testing, road testing, and real projects. The actual related coefficient alpha and the payment related coefficient n were determined. According to the Chinese specification, alpha and n are dependent on the design criteria for asphalt payment, while they are independent on the design criteria for concrete payment. Asphalt payment design criteria are denoted by ASP1, ASP2, and ASP3, which will be detailed in Chapter 5. For ASP1, ASP2, and ASP3, n equals 4, 5, and 13, while alpha values are dependent on the axle types as shown in the table. For concrete payments, however, n equals 16 and alpha equals 1, which is independent on the design criteria and axle types. Those two figures show the ERFs for the two single axles. Those three figures show the ESOs for the three tandem axles. Those two figures show the ESOs for the two tandem axles. Now we learn an example. For type 2 axle of 80 kilonewton, from this figure, ERF is 0.41, 0.33, 0.055, and 0.028 for different payment conditions. It is obvious that damaging ability of the axles are different for different payment design indicator. Track factor is another concept which is a factor to convert track axles into sand axle, as shown in this figure. A truck has 3 axles, which are type 1, type 2, and type 7. ERFs are 0.5, 1.5, and 6.0 for those 3 axles. Track factor TF equals 0.5 plus 1.5 plus 6.0 equals 8.0. In other words, this truck is equivalent into 8 sand axles. Now, let's come back to our topic, ESO. In payment design, accumulate the ESOs on the design line driven the service life is used for determining payment structure thickness. There are 2 basic methods, namely ESO-based method and TF-based method. There are 4 steps for ERF-based method. Step 1, class the traffic days as shown in the third column of the table. Step 2, calculate the ERFs for different axles as shown in the second column. Step 3, calculate the ESO for different axles as shown in the fourth column. Step 4, calculate the total ESOs as the sum of the ESO of different axles. Following the 4 steps, accumulative ESOs of this example can be easily calculated as shown in the table. There are 4 steps for TF-based method. Step 1, collects the traffic data. Step 2, calculates the TF for different vehicles as shown in the third column. Step 3, calculates the ESO for different vehicles as shown in the second column. Step 4, calculates total ESOs as sum of ESO of different vehicles as shown in the fourth column. Following the 4 steps, the cumulative ESOs of this example can be easily calculated as shown in the table. Okay, that's all for today's lecture. Appreciate your listening, and see you next time.